So you're at a family reunion with a child sitting next to you that you assume is related to you in some way. And that child is in that phase where they ask the question,
Why? 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 Why?
over and over until they reach the limits of your minute comprehension and trap you in a cocoon of your own ignorance, where you just have to shout at them, please, that's just the way the world is. Now would you please shut up and let me eat Aunt Eris's potato salad in peace? The question that this annoying child has landed on today is,
Why is the sky blue?
well, why is it? What does light have to do with it? And most importantly, who does this child belong to? Welcome to Bad Astra.
Fine, let's get to the science content.
And it's exactly what it sounds like.
Stop!
We need to talk about polyamory.
I'm secretly a black hole.
Do they finally need me to captain a starship? Yeah, honey, that makes perfect sense.
Isn't physics fun?
Further study is needed. Let's begin with radiation. Light is one of the most interesting things in science because it's what allows us to see things, both on a daily basis, if you are fortunate enough to still have your eyes, and on a large scale with telescopes that image amazing nebulae and stars. Light is made of tiny little things called photons that travel as particles and as waves, but only recently imaged as doing both at the time of filming. Light is electromagnetic radiation, from gamma rays and X-rays to microwaves and radio waves. But visible light is a small range of wavelengths in between infrared and ultraviolet. Visible light is what humans can see, and is significantly less dangerous than the higher frequencies of electromagnetic radiation. Remember to always wear sunscreen, ideally 50 SPF and above, or else your skin might burn and you'll have a higher risk for skin cancer. The electromagnetic spectrum is all based on the wavelength of the light, which also affects the color we see. For a wave, the speed of the wave in a medium is equal to the wavelength multiplied by frequency. Since we know the speed of light for a vacuum or any given medium, we can easily calculate either the frequency or the wavelength from the other. So, for the sake of this video, frequency, wavelength, and color all mean the same thing. When you look at a red leaf, you're seeing photons with wavelengths between 620 and 750 nanometers, with frequencies around 430 terahertz, reflecting off the leaf and traveling into your eye. Higher frequency photons have shorter wavelengths, and lower frequency photons have longer wavelengths. Since higher frequency photons have more energy, they are more dangerous, and you therefore need to watch out for light with shorter wavelengths. That sunscreen we mentioned earlier mainly protects you from ultraviolet light. So let's talk about the other essential part of seeing, the eyes. If you are so fortunate as to still have them, your eyes have two different detectors that allow you to see, the rods and cones. Rods detect the brightness of the light, and the cones detect the color. They send a signal to your brain, which your brain interprets, and boom, you can see. However, most people only have 3 different colors cones can detect. These are red, green, and blue, the primary colors of visible light.
But I thought that the primary colors were...
Yeah, kid, your art teacher is a liar. The primary colors of ink, magenta, cyan, and yellow. Nowhere are yellow, blue, and red real primary colors. That's for another video, though. So, if we only have red, green, and blue cones, how can we see the entire rainbow? Well, your brain is really good at making sense of the signals. So, if you're looking at something yellow, your red and green cones both get the signal. Your brain interprets that as yellow, because that's what's in between red and green on the electromagnetic spectrum. Depending on how activated the different cones get, your brain figures out the color from there. In fact, color televisions are made with just red, green, and blue lights, all really small and really close. If you get really close to the screen, you can see the individual little lights. But when you sit back on the couch, you can see the picture in full color, thanks to your brain and physics. However, sometimes your brain creates things that aren't there. Let's take a look at the visible light spectrum. What if only your red and blue cones get activated? What's right in between? Green. But you have a receptor for that color already, and the green cones aren't getting activated. So how does your mind make sense of the red and blue cones going off? It makes up the color magenta. That's right, folks. Magenta light doesn't actually exist. When you see the color purple, the object is not reflecting magenta light. Your brain essentially decides that when in doubt, choose C and hope that's right. I should also mention that visible light is human-specific, because we're the ones doing physics. As amazing as it would be to have a labradoodle doing science, it would also be pretty dangerous because dogs don't have opposable thumbs. In fact, dogs can see fewer colors because they only have blue and yellow cones. But there are animals with many more cones, like the mantis shrimp. They have a total of 12 color receptors. Why? Scientists don't know. They can also punch water so hard that it boils around their tiny little pinchers. Prime example of the horrors of the ocean. But what about color blindness in humans? Do colorblind people have fewer cones like a dog? Nope. Your colorblind friends still have all 3 cones, but depending on the type of color blindness, it's either caused by an issue with the cones or with the connection between the cones and the brain. This is caused by a non-dominant trait carried by the X chromosome, which is why colorblindness occurs more frequently with people assigned male at birth, because they only have one X chromosome most of the time. So, is the sky blue because the sky reflects blue wavelengths, like the red wavelength reflects off the red leaf? But the air is clear, ideally. Honestly, it's a bit more complicated than that. So let's talk about scattering, absorption, and emission first. Scattering is when photons from a beam of light collide with atoms and bounce off in different directions. This affects the intensity of the light beam, because some of the photons have scattered off and are going their own ways. Sometimes these photons end up never being seen again, but that's because of absorption. Same setup. A photon collides with an atom, but a different kind. And this time, the kinetic energy from the photon slamming into the atom gets the atom really excited, and it starts vibrating now that it has absorbed the proton. That excitement shoots one of the atom's electrons up to a higher energy level from the pure elation of being touched by a photon after months of quarantine. When that vibrating atom knocks into other atoms, they start vibrating as well, and that kinetic energy is changed into thermal energy, or heat. I think I need a drink after that. Absorption is how the sun warms your skin, and how plants eat sunlight in a process called photosynthesis. The specific photons absorbed depend on the chemicals the beam encounters, because only photons with frequencies that suit an atom or molecule's discerning taste can be devoured. Why do different chemicals have different tastes in photons? The electrons in atoms and molecules can only exist at very specific energy levels, dependent on the chemical. So only a photon with the energy exactly equal to the difference between 2 levels can be absorbed. Think of these levels like a set of stairs, and photons like yummy energy bars. An electron can start on the first stair and either jump to the second stair or third stair, but can't jump between stairs. And atoms aren't allowed to eat multiple energy bars or have any energy left over. It's not a perfect metaphor. So only photons with the energy of exactly 1 small stair jump or exactly 1 large stair jump can be converted into jumping energy. And since every chemical has a different set of stairs, they all have different favorite flavors of energy bar. Because different chemicals have different favorite energy bars or absorbed photons, we can figure out what things are made of through the power of spectroscopy, or the study of light. In fact, this kind of science helped us figure out what our sun is made of. We took a look at the sun's light and split it into the spectrum, like how we can use prisms to make a rainbow. Then, we looked for gaps in the rainbow. These wavelength gaps show up like black lines on the spectrum because that light is being absorbed by the sun's atmosphere. Match up those absorption lines to the elements that create the same absorption lines, and boom! We know what the sun's atmosphere is made of through rainbow detective work. And it's not just the sun that does this. Theoretically, anything that you can shine a light through can give you this information. What about emission? Think absorption but backwards. After that atom gets excited, it has to cool down. Electrons are very scared of heights, so the electrons that jumped onto the higher stairs, either from absorbing a photon or getting thermally excited by some heat, jump back down to their comfort zone almost immediately. To do this, they have to give up energy in the form of those photon energy bars. That return to the lower energy level emits a photon in a random direction at a frequency that is the exact difference between the hot and heavy level and the cool down level. You can toss the energy bar in any direction, but it must be the right flavor. Again, different chemicals have different energy level staircases, so only photons with a few flavor wavelengths can be emitted by any given chemical. Astrophysicists refer to a chemical's favorite photon flavors as their fingerprints, since they're unique for everyone and leave a trace. Because of how specific those fingerprints are, we can again use our rainbow detective work to figure out what things are made of. Now we're looking for the presence of additional colored lines from the emitted photons, instead of gaps from absorbed photons. Here's some bonfire fun. In order to see emission lines, you need to get the atoms excited. An easy way to do this is thermally. Set the thing on fire. To get those emission lines, set your desired element on fire and watch the flame's color change. In fact, a lot of stores now carry packets of stuff that you drop in a fire to make the flames turn blue or green or purple. Wow, those middle schoolers were right. Physics is pretty gay. A beam of light, especially one coming from the sun, is composed of a ton of photons, in the way an ocean is composed of a ton of water droplets. Adding to the chaos, scattered and emitted photons are sent in effectively random directions. So instead of looking at why a single photon with a wavelength of 700 nanometers is doing what it's doing, and what the result is, we look at all the photons within a range of wavelengths, associated with a color. So we would think of all the photons with wavelengths of 620 to 750 nanometers as red light, because science uses the metric system. America. At this point, your annoying child relative has probably stopped listening. But if they haven't, and they're asking you,
What does all of this have to do with my original question? Why is the sky blue? Did I really need all this background information to understand the answer to such a seemingly simple question?
here's your answer. Fancy scattering. There's this specific type of scattering called Rayleigh scattering that basically means in our atmosphere, since nitrogen and oxygen molecules are way smaller than the wavelengths of visible light photons, photons with shorter wavelengths scatter easier than photons with longer ones. Or, to use science words, the amount of scattering is inversely proportional to the fourth power of the wavelength. The point is that when a sun's light enters the atmosphere and bumps up with a bunch of nitrogen, oxygen, and other trace elements in our sky, the shorter wavelengths, which are on the violet side of visible light, scatter easier than the reds and oranges. These shorter wavelength photons bounce in random directions all around the atmosphere or sky. Eventually, some of these photons are knocked in your direction and collide with your light detectors, those rods and cones. Scandalous. Because shorter wavelengths are scattered most around the atmosphere, they're what we see when we look up at a random part of the sky. The sun still looks yellow because most of its light, which happens to include mostly yellow wavelengths, never gets scattered at all. It just travels in a straight line to the ground, or your eyes. No, please do not look directly at the sun.
But if violet is the shortest wavelength, and the shorter the wavelength, the more it scatters, then why isn't the sky violet?
Well, surprisingly astute child, it's because humans suck at seeing violet because the sun emits less violet than blue light, and because violet light tends to be absorbed by the upper atmosphere. Purple, the mix between red and blue, is a bit easier to see, but that's not a true violet. UV light is closest to actual visible violet light, but you shouldn't look directly into a UV light because you can damage your eyes. In fact, a Chinese rave once got the wrong kind of UV lights and bought the kind typically used for sanitizing medical equipment. Everyone left with severe sunburns and eye damage as a result. So again, don't look directly into even the weakest of UV lights. So, Since blue is the shortest wavelength range with enough initial photons and which we can easily see, the sky appears blue. Sky blue is your brain's interpretation of the combination of those shorter wavelengths, specifically the ratio of red, green, and blue light that hits your cones. If you look at the sun and see that it's yellow or white, that light is traveling directly from the sun to your eye without scattering. And may I just say again, please do not stare into the sun without a solar filter or eclipse glasses. You will damage your eyes. Only idiots look directly into the sun without a proper filter. All right, kid. That's why the sky is blue.
But why are clouds white?
Because water vapor particles are way larger than visible light wavelengths, and therefore use a different fancy scattering called me-scattering. This type of scattering scatters all photons about the same, regardless of wavelength. Therefore, you see an even spread of photons coming from those clouds, which your brain interprets as white. Now, seriously, who are you related to here?
Wouldn't you like to know, weather boy?
Astra out.